several decades ago, I did my master's thesis to introduce tune mass dampers for tall buildings, control of motion. And you need 3 people to serve on your committee. And those of you who have done all these things. And I went to one of the guys and I told him, and he asked, what is the topic of your research? And I told him about it, and he said, oh, that's a crazy idea. I can't serve on a committee like that. And today we see how many buildings have tune mass dampers. So with this concept here, again, it might sound a little crazy, but I think it might have some future in this application. That's using the motion of building indirectly to harvest energy. So basically, with the background, some power estimations, regenerative TMDs, TMDs in series, and some experimental demonstration of energy harvesting from tune mass dampers I'll talk about. So quick one. Everybody knows about energy crisis. The topic or the theme of this conference is sustainable green energy for tall buildings. 2 options are we have solar or wind, and you heard some of the examples. Here's a tower which has solar panels on it and can generate 21 kilowatts of power. We have buildings, as was discussed this morning, also with windmills, and they have the capacity with 3 turbines in this particular case, 225 kilowatts. Though it's not a very large amount of energy, but still, you don't have to burn the carbon footprint generated power in regular case. So many of you have seen these self-powered systems. For example, in case of helicopters, if in order to monitor the health of the blades, because the blades are moving, so they put some devices which will generate power to feed these sensors, because something rotating, you can't have a cable taking up power on that one. In plants, sometimes they use temperature to harvest energy to look at the performance of these facilities. And as you can see, you might have seen these kids with the shoes. You have seen these roller carts also with little lights blinking. And in the defense, they have also, there's a lot of gadgets on a soldier. So there's a little, because of your motion of the knee, you can generate, this is not mega, this is milli watts. So that is the level of energy you can see. So if you look at a survey was done, the energy harvesting is very popular in mechanical engineering. And in mechanical engineering, they're dealing with smaller things, compared to us with the super tall buildings. So even a small amount of energy is good enough to do certain feeding the sensors and stuff like that. So 44% of the energy is right now being harvested, or energy harvesters are based on this type of devices, while other 2 are, well, photovoltaic is quite large, and then these 2 others. So vibration, light, and heat are the 3 main sources. And if you look at the number of these studies over the years in academics, you can see very large number of increase in number of articles, even on harvesting energy from various sources. So the current research, mostly in mechanical engineering or aerospace, and a little bit of civil engineering now, is all based on 100 milliwatts, which is a very small amount of energy, but depends if you're using it to light up a sensor or something like that, it is good enough. But if you bring this idea to a building, guys, they'll say, this will create more hassle for me rather than to implement any device like this. Then we look at, as this is the theme of this conference, the buildings move with the wind. And, we have had cases in which glass broke. We also had a very large excitation, self-excited flutter type instabilities in case of long span bridges, where there's a very large motion. But we cannot let the buildings vibrate that much to harvest energy, because if that was possible, we will be in good shape. But the trouble is we have to use an indirect source in a vibrating building. And if you just look at some of the size comparison, you have already seen a lot of wind turbines this morning. 344-foot tall wind turbine creates only 1.5 megawatt of power. And we have structures which are much, much bigger, and they are vibrating all the time, a little bit in wind. So in order to, there is a two-edged sword here, because the buildings vibrate, we have to use a mitigation device, as the 2 previous papers were talking about, controlling the motion of these buildings. by auxiliary damping devices. So this is one example of a type A 101 where there's a very large damper, which is a pendulum type damper, which is a tune mass damper, which swings back and forth and controls its motion. Its weight is 730 tons, and there are viscous dampers which are connected because that is part of the system in a TMD. And if those of you are mathematically inclined, this whole thing can be represented by a building with two springs and a secondary mass with a spring mass system over there. So 730 tons of mass moves back and forth, and there's a lot of energy in that mass which can be utilized to dampen the motion. There are other examples for some typical 600 tons, 94 tons in case of a bridge, 600 ton, 410 tons. And I heard that this new building, Shanghai Tower, has a much higher value than this number for the tune mass damper on top of that building. So these masses are going to be moving. So there's energy available, whether we utilize it or not. So that is our, even in this case, this building also has a TMD. And so we want to use the TMD as a dual function for helping to keep the green energy and also dissipate the motion of the structure. So it's a dual function TMD, so it would harness the energy into, the motion into energy, and at the same time provide extra damping, which we have been all looking in this particular session. So power estimation, just to have some idea about how much is the actual power which is available in these tune mass dampers. I think that's like, just skipping this math, this is a very simple equation where power available in a tune mass damper would be depending on this relative motion, this motion of the building, x 2 dot square. So based on that, we did some analysis of some of the buildings with these TMDs. So this is the type of energy which is available, which can be harnessed if we use a proper way of capturing that energy. So this is one of the 8 dampers simulated response from type A 101, where we can generate about 74 to 132 kilowatt of power. Just to develop this technique, we just had this long chain of analysis where we model wind speed, which convert into the wind force spectrum. This could be done in a wind tunnel or can be done numerically. And then we find the force and look at the performance of the structure. Here is a typical record of wind over 5 hours duration. And we are just using a benchmark type building, which is 306 meter high and 42 meter width in one direction. So in this particular case, 85 kilowatts of power is available from harvesting, and for the high wind event of about 13.5 meters per second at 10 meter height. So in this particular measurements were done in Chicago, and I think 13.5 meter wind happens quite often in that most cities in certain parts of the year, and you have a lot of energy just being wasted into viscous dampers, and we are not utilizing them. So what is the solution? We have regenerative TMDs, and in this particular case, the building is a low frequency motion, so we have a TMD, and we can attach, instead of using that viscous damper, we use a regenerative damper, which will create energy and at the same time dissipate the motion of the structure. In order to further enhance the motion of the TMD, we can use, like in case of viscous damper, people use a toggle switch in order to increase the relative displacement. Same thing can be done through a ball screw type arrangement where we can increase the motion as far as it goes into the electric generation device. Here are various approaches we have in which we can synchronous machines which will help to generate that power from the motion of the building left and right. The trouble is that the building oscillates back and forth. So in other words, this ball screw has to also go back and forth, which is not a very good, efficient way of doing it. Can you put the first video, please? And here is this system, the little gadget we have developed, which helps So regardless of building going up and down, motion in one and two directions, oops, but as you noticed, that thing is only moving, the motor is going in one direction. So we are always getting the same type of input to the motor. There's another thing is that normally we use a single mass tune mass damper. There are two other versions of tune mass dampers. One is multiple mass dampers which are in parallel with the building. So you take this particular mass, you divide it into 10, and you have 10 little doodads which are attached to the buildings, and they are more effective and more robust, and they are being used in some buildings. But if you use two in series, that means the third mass or the second mass of the tune mass damper is connected to the first one. This device works even better because instead of using 730 ton for 101 type A, we could have done with 375. But there's a disadvantage is that the stroke of that thing becomes very large. It is 6 times more than the previous one. But again, it's a much smaller mass which is moving to that extent. So to avoid that, one could always use an electrical method. You could put an electrical system here which could mimic the third or the secondary tune mass damper in order to look at various levels of motion for the structure. So let's look at the experimental version in which how we had a tune mass damper on a small scale model of the building in which the motion of the tune mass damper through the rack and pinion system was converted into a motor. And as you can see, this is a frame of a building on a shaking table. And on top of that, we have these are 2 springs, and here's a mass which moves back and forth. And as you can see, as the mass moves back and forth, it moves that motor, which generates power. And could we see the video number 2, please? So we have 2 options. In one case, you will see these. Now it's going to be released. As the secondary mass moves, you can have those light bulbs. This is just used as a shunt to show that the power is being generated. Oops. Again, you know, we don't need to go through the math of all this stuff. There are 2 ways we can have a shunt, just like those 2 lights, to show somebody that the power is being generated, or we can just start having a charging circuit shunt in which the power can be accumulated, and this is in this particular case the power, the voltage generated, and the charging current which has been produced. And at the same time, you can see the building motion, which blue is without the damper, is with the damper, is red, is controlling. So we are having a damping. Basically, you're replacing your viscous damper, which is a part of a TMD, with this regenerative system, which is going to be providing damping as you need for the TMD. At the same time, the relative motion is generating power in another circuit. So we can have power generated, and we have the motion being controlled as far as that is concerned. So at the same time, reduction and the power is being generated. So the conclusion, a green building technology, dual function TMD, we can have a power from wind-induced vibrations, 10 kilowatts to 100 watts, more effective and robust in vibration control. And also we can do retrofit design. If you already have type A 101, we can go there and set up our system there. So each damper motion, we could replace them by this type of system, where we could be providing the necessary damping which is needed for that system, yet we would have be generating power. Potential to reduce the construction mass, and we have shown it at a smaller scale that this can be done. And I think there are other parts of the building which are also moving. Some cladding parts are also moving sometimes, not as much, but we can provide different type of harvesting devices. So whole building could be a source of power, and at the same time, it would provide you a way to control unnecessary vibration in the building. Once again, as I said before, about a few decades ago, TMD was the professor said that it's a very crazy idea. I don't want to serve on your committee. And I think if I go back, probably I'll have a similar comment on this one. But we have demonstrated this at a smaller scale, and it can be taken to next prototype level and go beyond where we could have the energy being produced and at the same time mechanical energy being dissipated, something which we all want to have more damping in our buildings. So it's a dual purpose TMD. And there could be other sources of way how we can tap into energy. We thought TMD was an easier way of doing that. We have a similar concept for tuned sloshing dampers, where you can have a wave bobbing energy harvester that may not produce that much energy, but as you know, all these sloshing dampers need to have some light. Otherwise, you will have a lot of algae growth in there. So in order to bring a new power light into that room, you can just have a little energy bobber, harvesting bobber put in the sloshing damper, and that would be creating light for needed in that room. At the same time, you will also know that your damper is in operation. With that, I'll close and thank you for your attention. Yeah.